Welcome to this lecture on complex analysis. Today, we are going to explore one of the most beautiful and powerful ideas in all of mathematics, analytic functions. Imagine a world where knowing the exact conditions at one single spot allows you to perfectly predict the conditions everywhere else around it. In the realm of complex numbers, this magical predictability actually exists. We are going to build your understanding of this concept from the ground up, step by step. Now that we have introduced the topic, let us understand what an analytic function actually is. Why does this concept matter? In the real world, things like weather are chaotic and unpredictable. But in mathematics, an analytic function is the ultimate well-behaved rule. It is a function that has absolutely no sudden jumps, no sharp corners, and no unpredictable breaks. It is so perfectly structured that if you know how it behaves in one tiny area, you can smoothly extend that knowledge outward to predict its behavior elsewhere. It is a rule for complex numbers that operates without any mathematical hiccups. Building on this idea of perfect smoothness, we need to define this more formally. In mathematical terms, having a derivative at just one isolated spot is not enough to earn the title of being analytic. The function must be differentiable at that exact point and at every single point inside a small circle surrounding it. We call this small circle a neighborhood. Think of it like a patch of smooth ice. It is not enough for just one single snowflake to be smooth. The entire patch around it must be smooth so you can safely glide over it. And if a function is analytic at every single point in the entire complex plane, we give it a special name, an entire function. So we know what it means to be analytic, but how do we actually test for it without checking every single microscopic point? This brings us to a powerful set of rules called the Cauchy-Riemann equations. To use them, we first break down our complex function into its real and imaginary parts. We use the letter u to represent the real part of the output and the letter v to represent the imaginary part. For the function to be differentiable and analytic, the way u changes must perfectly balance the way v changes. We find this delicate balance by taking partial derivatives, which means we look at how the function changes when we tweak only one variable while keeping the other completely frozen. Now that we understand the setup, let us look at the first of these two crucial equations. Conceptually, this formula ensures that the function grows consistently. The equation states that the partial derivative of u with respect to x must equal the partial derivative of v with respect to y. In plain English, the term on the left tells us how the real part of the output changes as we move horizontally. The term on the right tells us how the imaginary part changes as we move vertically. This equation demands that these two rates of change must be exactly equal. If the real part grows at a certain rate when moving left to right, the imaginary part must grow at that exact same rate when moving from bottom to top. This first balance is not enough on its own, which leads us to the second Cauchy-Riemann equation. This formula completes the test for analyticity. It states that the partial derivative of u with respect to y must equal the negative partial derivative of v with respect to x. Let us break down these symbols. The left side shows how the real part changes as we move vertically. The right side shows how the imaginary part changes as we move horizontally. But notice the negative sign. This means the vertical change of the real part must be the exact opposite or negative of the horizontal change of the imaginary part. If both of these equations hold true and the derivatives are continuous, the function is guaranteed to be analytic. Before we move on to a concrete example, let us visualize what these equations actually do. Here, you are looking at a diagram of a neighborhood around a point in the complex plane. The dashed circle represents the boundary of this neighborhood. Inside, you see two sets of intersecting lines. The blue lines represent the real part of the function and the red lines represent the imaginary part. Because this function obeys the Cauchy-Riemann equations we just discussed, notice how these lines always cross each other at perfect right angles. This geometric perfection, this orthogonal crossing everywhere inside the circle, is a direct visual result of the function being analytic. Now that we have seen the formulas and the geometry, let us test a simple mathematical function to see if it is analytic. We will look at the squaring function. F of z equals z squared. This is a very common function in physics. To start, we cannot just guess. We must systematically separate the function into its real and imaginary parts. We replace the complex variable z with its standard rectangular form, x plus I times y. Then, we expand this squared term using basic algebra rules, just like a perfect square binomial. Finally, we substitute -1 for I squared, which allows us to group the purely real terms together and the purely imaginary terms together. Continuing with our setup, we now have our function perfectly split into two distinct halves. We identify the purely real part of our function, which we call u. It is equal to x squared minus y squared. Now we need to find its partial derivatives. First, we take the derivative with respect to x. We treat y as a constant, so the y squared term becomes 0, leaving us with just 2 times x. Next, we take the derivative with respect to y. This time, x is treated as a constant, so the x squared term becomes 0. Using the power rule on the negative y squared term gives us -2 times y. Moving forward with our calculation, we must now shift our attention to the imaginary part of our function, which we call v. This part is equal to 2 times x times y. Just like before, we need to find its partial derivatives. First, we take the derivative with respect to x, keeping y completely constant. Since 2 and y are just constant multipliers, the derivative is simply 2 times y. Finally, we find the partial derivative with respect to y, keeping x constant. Treating 2 and x as constant multipliers this time, the derivative is simply 2 times x. We have now successfully calculated all 4 required partial derivatives. With all our derivatives calculated, we reach the final step, checking them against the Cauchy-Riemann equations. We check the first equation and see that both derivatives are exactly equal to 2 times x. The horizontal change of the real part perfectly matches the vertical change of the imaginary part. Next, we check the second equation. The derivative of u with respect to y is -2 times y, which is exactly the negative of the derivative of v with respect to x. Both equations are satisfied everywhere. Physically, this means the function behaves perfectly smoothly without any breaks. Therefore, we can confidently conclude that the squaring function is an entire analytic function. So, we have proven that the squaring function is analytic. This brings us to a different function that actually fails this mathematical test. We will test the complex conjugate function, f of z equals z bar. We want to see if this seemingly simple function is analytic, proving that visual simplicity does not always guarantee mathematical smoothness. By standard definition, the complex conjugate of x plus I times y is simply x minus I times y. This immediately gives us our separated real part u, which is just x, and our imaginary part v, which is -y. Continuing with our test of the complex conjugate, we now calculate the partial derivatives. For our real part, u equals x, the derivative with respect to x is simply 1. Because there is no y variable present, its derivative with respect to y is exactly 0. Now we look at the imaginary part, v equals -y. Since there is no x term present, its derivative with respect to x is exactly 0. The derivative with respect to y is simply -1. These are very simple constant derivatives, and now we are ready to compare them. Now we bring these final results together to see if they balance. We compare the derivatives using the very first Cauchy-Riemann equation. We can clearly see that the number 1 does not equal the number -1. The very first equation fails immediately. Because this required balance is not satisfied, the function is not differentiable anywhere in the complex plane. Physically, this means the function does not preserve the smooth, predictable structure required for complex modeling. Therefore, it is nowhere analytic, proving that just because a function looks simple, it does not mean it is mathematically smooth or well-behaved. Now that we have seen how to test for these functions, why do we care so much about them? In the real world, analytic functions are the secret language of physics and engineering. They are used to model anything that flows smoothly without being created or destroyed. For example, if you want to design an airplane wing, the equations that describe the smooth, steady airflow around it are analytic functions. Similarly, if you are designing a computer chip and need to know how heat will spread, or if you are mapping invisible electric and magnetic fields, you rely on these functions. They allow us to solve incredibly complex boundary problems with perfect mathematical precision. This brings us to the end of our journey. So let us review the key takeaways. We learned that an analytic function is a complex function that is smooth and differentiable, not just at a single point, but in an entire neighborhood. We discovered how to test for this perfect smoothness using the Cauchy-Riemann equations, ensuring the real and imaginary parts change in perfect harmony. Finally, we saw that passing this test unlocks powerful mathematical properties, allowing us to model the most complex, flowing systems in the physical world. You now have a solid foundation in analytic functions.